Hello. Today we're going to have a look at the first key area from the electricity unit in National 5 Physics, electrical charge carriers. So, the first thing that we need to deal with are the fact that there are two types of electrical charge, positive and negative. Now, if we have two opposite charges, then they will attract towards each other, whereas two like charges, like two positives or two negatives, will repel away from each other. And that's the principle through which electrical current works. So, first of all, a definition. Electrical current is simply the rate of flow of charge. In a standard electrical circuit, these charge carriers are electrons, but we don't talk about the rate of flow of electrons because that number would be astronomically huge. So we group electrons into groups called coulombs. So here's an electrical circuit showing the electrons, or the charge carriers, as they move from the negative terminal of the battery or the cell round the circuit and back towards the positive terminal. And the nice way of understanding what's going on here is if we think of it a bit like this penguin game. So the penguins climb up the steps, that's a little bit like the cell or the battery, and then they go around the circuit and back to the start again, and then repeat. So the electrons are a little bit like the penguins, the steps a little bit like the cell, and the slide a little bit like the circuit itself. So we can define the amount of charge flowing past a point in a circuit per second as the current. And the current is measured in amps or amperes for short. And on the formula sheet, we have this formula. Q equals I times T, which means that the charge measured in coulombs is equal to the current measured in amps multiplied by the time measured in seconds. Now, that is really just a different way of writing I equals Q divided by T, which is the definition of current. I equals charge divided by time. We can also use it to work out time, incidentally, the charge divided by the current. So, for example, a lamp has a current of 1.5 amperes flowing through it while lit. How much charge flows through the lamp in 50 seconds? So, just like any question like this, we'll start by writing our formula, Q equals I times T. We will put our numbers into the formula. 1.5 is our I, and times T, which is 50, and that gives us a charge of 75 coulombs. Now, there are different types of electrical current that can occur. What's called alternating current and direct current. So let's start with direct current. Direct current, or DC for short, is where the charges flow continuously in one direction. For example, from a battery. So here's a little picture here showing the charges flowing out of this battery around the circuit and causing a fan to spin. That would be an example of a direct current. The other type of electrical current is what's called an alternating current, or AC for short. And in this, the currents continuously reverse direction. And this is how mains electricity works. So for example, here we have the um, electrons continuously going back and forward around this circuit. And if we were able to look at a lamp at a very uh, short exposure camera, we'd be able to see that it actually flashes on and off repeatedly as the current repeatedly changes direction. Our mains electricity in the UK is has a frequency of 50 hertz, which means the current completes one cycle of forward and backward 50 times a second. Now, we can investigate how alternating and direct current looks by investigating it using an oscilloscope. An oscilloscope lets us see electrical waves. So, if we switched on the oscilloscope and adjusted the horizontal line on the oscilloscope so that it crosses the center line. This is effectively a graph of voltage against time. So voltage, or current, we can think of on the y-axis, and time along the x-axis. And the line there is along the center of the oscilloscope, indicating no current is flowing or the voltage is 0 volts. Now, if we connected the two terminals to the battery, to the Y input and the earth of the oscilloscope, what would happen is that line would move from the middle up towards the top. And that indicates that there is a steady current, but it's now no longer zero, it's a steady current in a particular direction. If we connect it now to the alternating current source, rather than a straight line, we get this wavy line. And you can see the wavy line begins in the center at zero current, and then it increases above the center, which indicates current flowing in one direction, then drops back down to the center, which indicates the current stops, and then increases away from the center in a negative direction, showing the current is moving in the opposite direction. So this wave shows the continually reversing nature of the current in a alternating current circuit. And that is effectively all we need to talk about as far as electrical current and charge goes. So I hope that was helpful. We'll be back with another video about electrical potential, potential difference, and electrical circuits another time. I'll talk to you again later. Bye for now.